Welcome again. Today we will discuss nickel, platinum and iridium based reagents in organic synthesis. So, if you see the periodic table, nickel is here, this is 4th row, and iridium and platinum, they are side by side, they are in the 6th row. So, first we will discuss nickel based reagents in organic synthesis. So, we will discuss alkene alkyne oligomerization, carbon carbon bond formation, epoxidation, then carbonylation, coupling of an enol alkyne and organozinc we will discuss. This is nickel catalysis, and nickel catalyzed cross coupling reactions also we will discuss, and cell higher olefin process, that is industry process, also we will discuss. So, organonickel chemistry is a branch of organometallic chemistry that deals with organic compounds featuring nickel carbon bonds. Organonickel compounds are short-lived intermediates in organic reactions, and the first organonickel compound was nickel tetracarbonyl NiCO4, reported in 1890 and quickly applied in the Mond process for nickel purification. Organonickel complexes are prominent in numerous industrial processes including carbonylation, that we will discuss, hydrocyanation and the cell higher olefin process, that also we will discuss. So, first we will discuss alkene alkyne oligomerization. So, nickel compounds catalyze the oligomerization of alkenes and alkynes. So, this is important, both alkenes and alkynes. One practical implementation of alkyne oligomerization is the Reppe synthesis. For example, in the synthesis of cyclooctatetraene, and this is a formal 2+2+2 cycloaddition. So, this kind of cycloaddition is only possible with metal catalysis. Like here, acetylene, if you put with nickel CN2 calcium carbide THF in 60 degree centigrade, you get cyclooctatetraene. Cyclooctatetraene. This is 8 pi electron system, so this is not aromatic. Formal 2+2+2 cycloadditions also take place in alkyne trimerization. This extensible trimerization can generally include benzene. So, this mechanism we will discuss in next slide. So, benzene is generated in situ from a benzene compound attached to a triplet and trimethylsilyl substituted in the ortho position. Here you can see this OTF and TMS is present, and with base, if you put base here, then you will get benzene. So, this is benzene precursor and reacts with a diene such as 1,7-octadiene along with a nickel to bromide zinc catalyst system NiBr2 bis diphenyl phosphinoethane zinc to synthesize the corresponding naphthalene derivatives. So, these are naphthalene derivatives. And when X is equal to CH2, then it is 1,7-octadiene, and this is the catalyst NiBr2 DPPE zinc, and this is the base solvent 80 degree centigrade, you get this. This was published in Chemcom 2005. This mechanism also we will discuss. So, first we will discuss Reppe synthesis mechanism, and Reppe synthesis we have already told that 4 molecules of acetylene will give cyclooctatetraene, and this is completely atom economic process. So, first step is that 2 acetylene motif bind to this, and then another acetylene can bind, and then this kind of cyclopentadiene nickel system. So, nickel cyclopentadiene will form. This kind of system we have seen with titanium. So, nickel can also do this, nickel cyclopentadiene, and then another molecule of acetylene can come. So, this kind of species will form. Then this alkyne inserts here to generate a 7-member rings. This is nickel cycloheptatriene, and this acetylene motif again will insert to generate this, and now nickel will coordinate with part. This is the double bond part, and then again another acetylene will come. So, nickel will coordinate with the double bond of a cyclooctatetraene, and it will coordinate with an external acetylene group, and now again another acetylene will coordinate it will, and then it can reductively eliminate. So, this is reductive elimination, and this is the product cycloheptatetraene, and you get this. This is the active catalyst system. So, this is the Reppe synthesis, that from an acetylene you can get cyclooctatetraene. Alkyne-alkane oligomerization, so that we will discuss the benzene one here. So, with nickel 2 first react with zinc to generate the nickel 0. Alkyne will coordinate with the nickel like this. We have already seen with acetylene. So, this kind of coordination will happen, and then fused nickel cyclopentadiene. So, earlier we have seen nickel cyclopentadiene, here fused nickel cyclopentadiene is formed, and now the benzene will come. So, this is benzene, and benzene will come, and then this it inserts here. You can see this is the benzene component, it is inserts here this bond, nickel carbon bond, and you get this. This is 7-member ring is formed, and now the reductive elimination happens. So, now reductive elimination will give this naphthalene derivative. So, this is the product, and you get this. This is the active catalyst here. So, 2 plus 2 plus 2 cycle addition here is happening, and you get the naphthalene derivatives, and these products are very useful, and this was published Chemcom 2005. Some more alkene-alkyne oligomerization. Now, the formation of organonickel compounds in this type of reaction is not always obvious, but in a carefully designed experiment, two such intermediates are formed quantitatively. So, you can form the intermediate also, that this kind of mechanism is operating, like this one with imine and this internal alkyne with nickel cord, tricyclohexyl phosphine and benzene, room temperature 10 minutes, you get this 5-member ring. And here you can see this is the alkyne component, this is the imine component, and this is the nickel. So, this tells that this 5-member ring with nickel is forming. Also with alkyne, then this 7-member will form, that another alkyne will insert, and after heating at 100 degree centigrade, reductive elimination happens, and you get this compound 6-membered heterocycle. N heterocycle is forming here. This was published in Angu on the Chemi 2007. Now, we will discuss other carbon-carbon bond formations. So, carbon-carbon bond formation is very important reaction in organic synthesis, and nickel 0. So, earlier also we have seen nickel 0 is the active catalyst. It can be in situ generated from nickel acetyl acetonate and zinc, catalyze the conjugate addition alkyl or aryl iodides to conjugated carbonic compounds under sonication. An interesting example is the methylation, which fails to take place under other conditions. So, this is the reaction. This is cyclopentanone 3 substituted, and with nickel acetyl acetonate zinc with methyl iodide ether 20 hours, you get 84% yield. So, this conjugate addition happens, and you get this quaternary center. So, this kind of reaction is difficult by other ways, because you generate a quaternary center and methyl group is adding in a conjugate fashion. This was reviewed in Encyclopedia of Reagents for Organic Synthesis, John Williams Sons by Leo Packet in 1995. In the presence of nickel acetyl acetonate, organozinc adds to phenyl acetylenes to give substituted alkenes with high stereoselectivity, greater than 99% syn addition. The resulting organometallics can be trapped with electrophiles. So, this is an important reaction. This is Negishi kind of reaction. So, this is internal alkyne diethyl zinc, nickel acetyl acetonate, CuCN lithium chloride, and then this is the electrophile. So, this is electrophile. And you get these compounds are very important. So, this compound is tetra substituted olefin. Substituted olefin. So, one ethyl group is coming from diethyl zinc, and this is the electrophilic component, and this is syn addition. This is also important, syn addition, and 71% is forming, and this is the ratio here Ez 98:2. So, the possible mechanism that this intermediate is formed, this intermediate is formed that this is the diethyl zinc that one ethyl group adds here and Zn(E2) adds here, and also this alkyne will be coordinated with nickel 0, because alkynes always like to coordinate with nickel, and then only this syn addition will take place, and after that this intermediate reacts with copper cyanide lithium chloride and this allylic bromide, and then this product olefin product is forming. This was developed by Paul Nochel, German scientist, and the paper was published in Anglo and the Chemistry International Edition 1997. So, some more reaction like epoxidation we will discuss now. The aerobic epoxidation of functionalized alkenes can be accomplished using nickel 2 complex in the presence of aliphatic aldehydes as co-reductant. For an example, nickel 2,1,3 diketonato complex catalyze the epoxidation of cholesterol derivative to give a mixture of beta and alpha epoxides in quantitative yield in the presence of isobutyraldehyde under molecular oxygen. So, this is the reaction. You can see this is the double bond here that will be epoxidized, and this is the catalytic system nickel acetyl acetonate oxygen, and isobutyraldehyde is converting to the isobutyric acid, and in this process you get the epoxidation of the double bond and two diastomers are forming. So, they are diastomers, and this product is forming major up epoxide 69% and down is 31%. Now, we will discuss carbonylation, that is also an important reaction carried out by nickel. Nickel complexes catalyze the addition of carbon monoxide to alkynes. The industrial production of acrylic acid at one time consisted of combining acetylene, carbon monoxide and water at 40 to 55 atmosphere and 160 to 200 degree centigrade with nickel bromide and copper halide. So, copper halide is the co-catalyst here, and example is acetylene hydrocarboxylation. This is acetylene and water, carbon monoxide, nickel bromide, copper X 160 to 200 degree centigrade, you get this. So, this is acrylic acid. So, this part you can see this is coming from carbon monoxide and water part. This was published in many journals. One of the paper is Applied Catalysis A Journal 2014. Also, the reduced-selective hydrocarboxylation of alkynes to saturated carboxylic acid can be accomplished using cobalt chloride, potassium cyanide and nickel cyanide under phase transfer conditions. Polyethylene glycol PEG4 is used as the phase transfer agent, and the branch saturated acids form as the major products. So, here earlier we have seen that double bond is there, but here we will see the complete saturation. So, with phenylacetylene reacting carbon monoxide with cobalt chloride, potassium cyanide, PEG 400 and nickel cyanide toluene solvent, potassium hydroxide base, you get this. This is the branch acid. Branch acid is more 56% yield, and this is linear acid. This is forming only 2% yield. So, first we will discuss the mechanism of the acetylene hydrocarboxylation. So, most likely nickel 0 is there as the active catalyst, and this mechanism has been shown with formic acid, but this can be considered as carbon monoxide plus H2 also. So, this active intermediate is formed, and here you can see there is a nickel hydride species is there. So, this nickel hydride, that is actually reducing the acetylene, and now this olefin is coordinated with the nickel. So, this nickel hydride species, that is reducing the acetylene, and you get a vinyl species now, and this vinyl species will react with carbon monoxide. So, the carbon monoxide insertion will happen, and this species will form, that is D, and in the D you can see the carbon monoxide insertion happens, and D, then the reductive elimination will happen. So, this reductive eliminations will give this. This is actually anhydride kind, and after elimination of carbon monoxide you get this acrylic acid. So, this is the product, acrylic acid. So, main thing is that H2O carbon monoxide reacts with nickel 0 to generate this nickel hydride species along with this, and that hydride, when acetylene is coordinating, then it is converted into the vinyl species, and then carbon monoxide comes. So, carbon monoxide inserts into this bond. After reductive elimination you get this anhydride, and after anhydride you get the carbon monoxide as well as the acrylic acid. Now, we will discuss carbonylation. So, this mechanism we have already seen carbonylation. So, carbonyl compound also you can generate. Carbonylation of allyl bromide catalyzed by nickel tetracarbonyl under an atmosphere of carbon monoxide. Like allyl bromide with nickel tetracarbonyl, also carbon monoxide external, and you get this acyl bromide. So, what is happening here? Here bond, one carbon monoxide has inserted, and then only you get this acyl bromide. So, this is very useful reaction. From allyl bromide you can get this acyl bromide. So, what could be the mechanism? So, here nickel tetracarbonyl will convert to nickel tricarbonyl. This is the active catalyst actually, active catalyst. And after reacting with allyl bromide, this carbon nickel bond will form either eta 1, or with one elimination of carbon monoxide the eta 3 species can form. This is the eta 3, because here this one carbon is attached, here this whole allyl system is coordinated with the nickel. So, this is eta 3, and they can equilibrate also after one molecule of carbon monoxide, because here 3 carbon monoxide is there, here 2 carbon monoxide. So, one elimination carbon monoxide will give this, alternatively addition will give this. Now, this insertion will happen. So, this insertion possible to give this 14 electron species. Alternatively, here also the insertion can happen from this intermediate also, one carbon monoxide goes this and you get this, and for this to this you need one molecule of carbon monoxide, that is also possible. Carbon monoxide comes, and after reductive elimination you get this acyl bromide, and you get this nickel tricarbonyl, you get back. So, this is the reductive elimination happen, that this component and this component bromide is giving the acyl bromide. This was published in JACS 2003, page number is 10412. Another important reaction carried out by nickel is coupling of an enone, alkyne and organozinc. This is very important reaction, 3 component reaction. The addition of organozincs to enones in the presence of nickel catalyst is one of the most important methods for effecting conjugate additions to two sterically hindered enones. Like here, this is cyclohexenone, this is phenylacetylene, and butyl lithium zinc chloride. So, in situ you will get but zinc, and with nickel cod 5 mole % catalyst you get this. So, this is very important that the conjugate addition of alkyne to the enone is happening, followed by the addition of the zinc species to the triple bond. This group and this group are the syn. So, they are syn addition, and this product you get 65% yield. So, this is very important. 3 component reaction, this is called 3CR. Also, if you have a alkyne with the enone itself, then also this kind of reaction will happen. And here if you see, this carbon is adding to this carbon, so that 1, 2, 3, 4, 5, so that 5 member ring is forming, and after that this terminal carbon atom of the alkyne, your zinc species, that is the diphenyl zinc, will add, and you get this product. So, here also syn addition. So, that means some cyclic intermediate is there, that we will discuss, that is why you are getting this syn geometry, and this product is formed in 76% yield. Also, if you see this one, there is a heterocyclic motif, and this is the alpha beta unsaturated ketone. So, this is acyclic enone, cyclic enone, and these two are cyclic enone. So, acyclic enone also, it can do the reaction with this alkyne. Here dimethyl zinc will form in situ nickel cod 5 mole % only, you get this. So, here also this carbon is attacking here 1, 2, 3, 4, 5. So, this 5 member is forming, and this terminal carbon atom there, this methyl group is adding, and you get this product in 74% yield. Also, this one you can see the oxazolidinone motif is there here also. So, these are all ketone, this is oxazolidinone. So, this carbon will react with this carbon. So, 1, 2, 3, 4, 5 member ring is forming, and this terminal carbon, there this dimethyl zinc will add, and you get this methyl, and here also the syn addition, and this product is forming in 87% yield. So, all cases the syn addition is happening, this is in general. So, different enone, not only cyclic enone, acyclic enone can also be used in this 3 component reaction, and you can get this cyclic product sometimes. If you have the alkyne and the enone in the same molecule, then you get the cyclic compound. This was reviewed in Account Chemical Research 2000, page number is 467. So, what could be the mechanism of an enone, alkyne and organozinc? If you have a enone, this is actually enone and alkyne are in the same molecule. We have seen also earlier that they can be in the same molecule, and with nickel 0, this kind of thing is happening. So, this carbon is adding to this carbon, so that 5 member ring is forming. So, this one and this carbon is coordinated with the nickel, and nickel is there. So, 5 membered cycle is formed, and this process is called oxidative cyclometallation. So, oxidative cyclometallation is happening here, because nickel is going to nickel plus 2, and now zinc will come here. Here the zinc, that R3 group is coming to the nickel, and this is bond is breaking, and you get an enolate here. There the R3 Zn group is coming, and this process is called sigma bond metathesis. Sigma bond metathesis. And now the reductive elimination happens. So, after reductive elimination, what will happen? This, of course, this will go to the enol and enol will go to the carbonyl, and here this reductive elimination happens, nickel eliminates and R3 adds here. So, what happens? The R3, because nickel is adding to this side, R3 can come through only this side, and that is why the selectivity is coming. So, R3 can only come from the side of nickel, and this kind of reductive elimination happens when L is equal to THF. So, ligand, this ligand, if it is THF, that means THF solvent, this kind of product is forming. Alternatively, if you use external ligand like triphenyl phosphine and R3 is equal to ethyl. So, ethyl, if you see, this can convert to ethylene also. So, ethylene, that is the beta hydride elimination. After beta hydride elimination, the hydrogen will come here, that is also coming from the nickel side. So, when THF is there, then the reductive elimination will give the component with the alkyl zinc. On the other hand, if ligand is triphenyl phosphine and R3 is equal to ethyl, that is diethyl zinc, then the beta hydride elimination can happen and you get this hydrogen here. So, here all substituted olefin, here tri-substituted olefin is forming, and this was also reviewed in Account of Chemical Research 2000, page number is 467. So, now we will discuss transition metal catalyzed cross coupling reactions. So, these are the overall cross coupling reactions, Rm, R-X, nickel or palladium, you get this cross coupled product. So, Negishi RZNX is the component, Rm is RZNX, Suzuki RbR2, Stille RSN, alkyl hole 3, Kumada RNGX or RLI, Hiyama RSI R3. And some cases alkyl like boronic acid we already discussed, alkyl can be used. Stille we have discussed aryl mainly, but Kumada alkyl can be also employed, and Negishi we did not discuss any alkyl. So, here with nickel we will discuss, with nickel you can use the alkyl. So, that is an important discovery in Negishi coupling. So, these methods have been extensively used for aryl allyl, aryl alkynyl, alkynyl alkynyl couplings, high functional group compatibility and limited use of alkyl electrophile. So, this is important. So, nickel chemistry can solve this problem, that alkyl electrophiles can be used, and this was reviewed in metal catalyzed cross coupling reaction, A.D. Mejeri and Didrich, Willie VCH, New York 2004. This is an book. So, Nochel first found this alkyl-alkyl Negishi coupling. This is an important discovery, and he found that if you have this alkyl bromide and if a double bond is there. So, this is very important. If a double bond is there in the substrate, then only with diethyl zinc, lithium iodide 20 mole percent and nickel acetyl acetone is 7.5 mole percent at minus 35 degree centigrade in THF solvent, you get this cross coupled product. So, bromine is displaced by ethyl, that is the Negishi coupling is happening here, and with R is equal to pH you get 81% yield, R is equal to butyl you get 82% yield. So, this method is quite efficient. Now, whether this olefin is important or not, that is what he performed another experiment. Actually, this olefin is now saturated. So, this is alkyl group, and similar substitution are there. Now, with diethyl zinc and identical conditions, lithium iodide THF minus 35 degree centigrade, even start at room temperature also, you do not get this. So, this did not happen. This product did not form, that is cross coupling did not happen. What happened? This Br is converted to ZnBr, and this product is formed, that is the zinc species is formed in 85% yield when R is equal to phenyl, and also similar yield when R is equal to butyl. So, that means when there is a olefin, then only the cross coupling reaction is happening. Without olefin, the cross coupling will not happen, and this tells that nickel only can bind with the double bond, and that is why it is facilitating this negacy coupling. We will see the mechanism. So, this was published in Angwan the Chemistry 1995, also JOC 1999. So, what could be the mechanism for this nickel catalyzed alkyl negacy reaction? So, this is the starting material, X is equal to bromide, but iodide, other things also can be used. And now, nickel acetyl acetonate is converting to NiL2, that is the nickel 0, and now it can coordinate. So, it can displace the halide and it is coordinated with the double bond. So, this is very stable, because when it is coordinated in double bond, it is quite stable, and now the zinc will come R2Zn. So, this species will form and ZnRx will go out. So, this species is formed, this is also coordinated with the double bond. Now, this can be equilibrium with this, there is no coordination, but this is unstable. So, when there is no coordination, then this is unstable, and if it is unstable, then only the transmetallation will happen with R2Zn, and you get this Znx. So, no cross coupling, because this is unstable, and this carbon nickel bond will react with the diethyl zinc to generate this zinc species. So, zinc will react here. Alternatively, if this is stable, then the reductive elimination will happen, and after reductive elimination you get this. So, this is the desired product, desired cross coupling product. Negacy coupling can be performed, and this shows the papers we already told. Now, what is the substrate scope for alkyl negacy reaction? Like here, this is the iodide now, and R2Zn, THF, NMP. This is the NMP, N-methyl pyrrolidinone, and nickel acetyl acetonate 7 mole % minus 35 degrees centigrade, and you get this cross coupled product. So, R is coming from the zinc, and what is the scope here? You can see this R dash is equal to butyl and R is equal to N pentyl. So, both are alkyl, that is the major thing here, and you get this 72%. Here this is phenyl, this is also N pentyl 80%, here phenyl, this O p phenyl group is present, also you get high yield 90%. Not only this kind of terminal olefin, internal olefin also can be used. So, this is terminal and this is internal olefin with an CO2 ET group, of course, conjugated, and here also this reaction happens, and N can be 2 to 3 with the same condition, THF NMP 2:1, nickel acetyl acetonate 7% minus 35 degrees centigrade, you get this cross coupled product. And here also you can see defined R group can be used, CH2O3 OP phenyl giving 79%, N pentyl giving 83%, CH2O6 OP phenyl giving 73% yield. And this is the papers Angwan the Chemistry 1995 and JOC 99. So, what we have seen that both terminal as well as internal olefin conjugated with an ester group can be used for this negacy coupling reaction. So, extension of Nochel's methodology. Now, it is important that if you do not have the olefin component in the substrate, whether you can use an additive, that is important. And he found that this also idea nicely works. Suppose this is iodide, this is a zinc. Of course, here no olefin is present, no double bond. And nickel acetyl acetonate 10 mole %, THF NMP 2:1, additive minus 35 degrees centigrade. Now, this is the additive. So, this is the olefin that of course will coordinate with the nickel, and it is not with the substrate, but it is additive. So, you can remove later and you get the desired conversion, that is important. The negacy coupling is happening, and you can see here this bond, if you break it, that this part is coming from the iodide and this part is coming from the zinc, you get 64% yield. Here also the dithion motif iodide and n-pentyl zinc, you get 78%. Here the ester group is there and this is the iodide here and n-pentyl zinc, you get 72% yield. Here also secondary, and you get good yields for this product. So, this strategy is very useful, that if you have a olefin additive, then also you can perform this Negishi cross coupling reaction and different alkyl groups can be incorporated. This was published in Anglo and the Chem in 1998 and also JOC in 1999. Some more extension here. We can see not only the alkyl, so this is aryl. Aryl group can also be used, Ri, nickel acetyl acetonate, THF, NMP, and this is the additive. So, this is additive and you get this cross coupled product in 71 to 80% yield. This was published in JACS 1998. Now, benzylic group can be also used. Benzylic group, that is the benzylic zinc bromide here with Ri, and you get this product under the same condition, only additionally you can use tetrabutyl ammonium iodide 3 equivalent, and this is now in 20 mole percent this olefin. So, it is not 100 mole percent, in this case 20 mole percent, and you get this cross coupled product. This was published in Organic Letters 1999. Also here bromide is there. So, bromide and these are iodide. Here also this reaction happens at dash 1 degree, 2 degree with this 20 mole percent additive and tetrabutyl ammonium iodide, use 3 equivalent and you get this products in good yield. And this was published in JOC 2002, page number is 79. Kumada coupling now we will discuss. So, nickel catalyzed CC cross coupling of Gigner reagents with alkyl, vinyl or aryl halides provides an economic transformation, but the reaction is limited to halide partners that do not react with organomagnesium compounds. One example is in the industrial scale production styrene derivatives, and the Kumada coupling is the method of choice for the low cost synthesis of unsymmetrical biaryl. So, here in normal Kumada coupling we will use the aryl iodide, because the Gignard will not react with the aryl iodide, but aliphatic iodide the Gignard will react. So, that is a drawback, but with nickel we can solve that problem also. So, this is the aryl halide, aryl magnesium bromide, nickel cord, this is the phosphine oxide, and you get this cross coupled product. And the proposed catalytic cycle involves oxidative addition followed by reductive elimination via transmetallation and cis trans isomerization. This is the mechanism, nickel 0 and Rx. This is similar like palladium chemistry, this Kumada coupling reaction. Here first step is the oxidative addition will happen and Rx comes, and now the transmetallation will happen. So, R dash will incorporate with nickel now, and MgX2 will be byproduct, and now cis trans isomerization will happen. So, there will come in the cis position now. So, the reductive elimination will be facilitated, and after reductive elimination you get this product and nickel 0 will be regenerated. So, Kumada coupling of alkyl halide with alkyl magnesium chloride and important influence of 1,3-butadiene on the reaction has been noted. So, this is very important, that earlier we told that alkyl halide cannot be used in Kumada coupling because Gignard will react. So, what discovery is that with nickel chloride and 1,3-butadiene if it is there, then you can get this cross coupled product. So, this is the cross coupling. So, if you do not use this system, what will happen? This can give a metal halogen exchange also. MgBr can be formed, right, and that will create problem. But it has been found with nickel chloride and 1,3-butadiene. So, this is also important. This is Cambe, that we will discuss its mechanism also, developed by Cambe, and this product is formed in 100% yield. So, the proposed mechanism for acceleration of the reaction with butadiene, of course, this nickel 0 will coordinate with the butadiene, and that is the oxidative addition will happen, and you get this kind of system. Nickel is nicely sitting between two allyl system. So, it is very much stable. And now the transmetallation will happen. So, this is the transmetallation, and R will coordinate with the nickel. So, nickel comes to the terminal carbon now, and this R group from the Grignard, and then this is forming, and after that R dash X will come, R dash X also will react with nickel, and you get this species, and after reductive elimination you get the cross coupled product. So, this is the product. So, the cross coupled product is forming here after reductive elimination. This was published in JACS 2003, page number is 5646. So, what is the scope of this reaction? Alkyl Kumada coupling, the scope, cross coupling of primary alkyl halides and Grignard reagents. So, here Rx, R dash MgX, nickel chloride, 1,3-butadiene, you get this. X is equal to can be fluoride, chloride, bromide. So, all halides can work, and you get this cross coupling product. Also, alkyl fluorides can also be used as the coupling partners. So, RF also can be used. So, this is very important, that alkyl fluoride can also be used in this Kumada coupling, and catalytic nickel chloride or copper chloride also, and 1,3-butadiene, you get this cross coupled product. This was published in JACS 2002. Now, substrate scope, that what we are looking for, what kind of substrates can be used for this nickel catalysis Kumada coupling. So, this is the Rx. So, this is the bromide, alkyl bromide, this is tosylate, this is bromide, this is chloride and fluoride also. And what kind of Grignard? Generally magnesium chlorides are used, N-butyl magnesium chloride, because they are less reactive than bromide. N-butyl, ethyl, isopropyl magnesium chloride, N-butyl, N-propyl. And 1,3-butadiene, you can use mole percent. Earlier also you have seen the additive. You can use mole percent, like here 10 mole percent 10, here 30, 30, and octyl chloride you have to use 50, and when it is fluoride then 2 equivalent. So, this is important because fluoride are unreactive substrates. So, for that you need 2 equivalent of 1,3-butadiene, and the yields are moderate to excellent. So, here in this case you get almost quantitative yield 100%. So, this method is very useful, that define alkyl bromide, alkyl tosylate as well as alkyl fluoride can be used, and you get this cross coupling products in good yield, and this was published in JACS 2002 4222, also JACS 2003 5646. So, changing additive allows dialkyl zincs to be used in the reaction, that is of course Negishi kind of reaction. So, just he found that whether this strategy can also work, that is the diene strategy, diene additive, and then he found that this kind of additive, there are two diene system and there is malonate moiety here, and this additive along with MgBr to 3 equivalent will give this Negishi coupling product in good yield. And with fluoride, earlier we have found that fluoride you have to use the 2 equivalent, but if you use this diene, then only 15 mole percent also is enough. So, here catalytic amount of additive. So, that means that this additive is better than 1,3-butadiene, because this additive only 15 mole percent is enough to give this Kumata coupling product dodecane 94% yield, and with NiCl2 this also works, but the yield is less. So, if you displace nickel acetyl acetone with nickel chloride, then the yield is less. This was published in Anglo and the Kevin 2004. Now, we will discuss cell higher olefin process. So, this is from ethylene you can get the higher olefin. So, this is an industry process for the production of olefins C12, C18 by ethylene oligomerization and metathesis. It is made by 3 steps: oligomerization of ethylene first, then the isomerization of C4, C10 and greater than C20, and then metathesis. Metathesis is important. We will see that in metathesis you can get higher olefins to lower olefins. So, higher olefins to lower olefin conversion, and the scheme of the process is shown below. This is the ethylene is coming, mixing, oligomerization, separation. So, you separate this C4, C10, C12, C18. Also isomerization you can do, greater than C20 here isomerization, here C4, C10 isomerization, then mixing, then less than C10 and greater than C14, you do the metathesis and you get the olefin C10, C14. So, this is an important thing, that different molecular weight olefins you get. Large scale industrial process incorporating olefin metathesis for producing linear higher olefins from ethene. So, this is the ethylene nickel catalyst. You can get this N CH2 CH2 N minus 1 CH is equal to CH2. So, this is the olefin and N is equal to 2 to 38. So, different higher olefins you can get. So, this is an important reaction, and the catalyst is prepared in situ from nickel chloride, diphenyl phosphinoacetic acid and a reducing agent sodium borohydride. There are 3 stages. First one in ethylene is oligomerized in the presence of the homogeneous nickel catalyst and 90 to 100 degree centigrade and 100 to 110 bar in a polar solvent like 1,4-butanediol to give a mixture of linear even numbered alpha olefins with a Fleury-Scholes distribution immiscible with the catalyst solution. So, this is the C4, C6, C8, C10, C12, C14, 16, 18, 20. And generally accepted mechanism of olefin insertion into a nickel hydrogen bond, that we will see. So, first this step is happening, this is the nickel COD2, and after that pH to P CH2COH, when it is reacting, because it is bidentate you can see. So, COD is eliminated, one COD, and now also you see this kind of one double bond is already reduced in this process also. And now this allyl system will coordinate with the nickel. So, this is the active catalyst actually, active catalyst, and this was published in Organometallics 1983. So, this is the active catalyst. So, after cyclooctene, so here cyclooctene elimination you get this, there is a vacant site and this vacant site will be taken by ethylene. So, after cyclooctene elimination you get this vacant site, there is of course a nickel hydride bond and then you get this, and now this hydride will add this kind of polymerization reaction we have seen already, titanium catalyzed, and here also this ethyl group is coming, there is a vacant site. Now, again this ethylene will come, this ethylene will go to this. So, the higher will form C4H9 now. So, like the C4, C6, C8, C10 all even number carbon atoms you get, because ethylene multiplication of ethylene. So, C4, C6, C8, C10 different olefin components you can get, and this is also K6 is phosphine PR3 is reacting with to the vacant site. This is side reaction. Now, further treatment of the C2N olefins, double bond isomerization over a solid potassium metal catalyst to give an equilibrium mixture of internal alkenes. This step is needed to increase the statistical distribution of the desired C10 C14 fraction. So, whatever we have got from the oligomerization, that is only the terminal olefins. So, this terminal olefins, if you want to isomerize, you have to use potassium catalyst, and you can see different isomeric. So, here it migrated to here, here it migrated to another carbon atom. So, this kind of isomers you can get. Metathesis state, the isomer mixture is passed over an aluminum supported molybdenate catalyst. The cross metathesis give a mixture of linear internal alkenes with both odd and even numbers of carbon atoms. So, after metathesis, now you can get odd and even. So, here you can see 2-butene, here another internal olefin doing cross metathesis. So, after cross metathesis, this part is adding to this part. So, this is become shorter now, and this part also is attaching to this. So, this is become shorter now, and now there might be possible of. So, this cross metathesis is very important, because here you can get the odd number olefins also. Now, we will discuss platinum based reagents in organic synthesis. So, first we will discuss Adam catalyst. So, Adam catalyst, also known as platinum dioxide, is usually represented as platinum oxide hydrate P2O2H2O. It is a catalyst for hydrogenation and hydrogenolysis in organic synthesis. This dark brown powder is commercially available. The oxide itself is not an active catalyst, but it becomes active after exposure to hydrogen, whereupon it converts to platinum black, which is responsible for the reaction. So, after exposure to hydrogen, it is going to platinum black, and that is the active catalyst for the reaction. So, how Adam catalyst can be prepared? It is prepared from chloroplatinic acid by fusion, or ammonium chloroplatinate by fusion with sodium nitrate. So, here you can see chloroplatinic acid H2PtCl6 sodium nitrate, you get platinum NO3 4. So, 4 NO3 is coming here, 6 NaCl, and 2 NO3 is going to 2 HNO3. And now, this platinum nitrate can convert to platinum oxide 4 NO2 O2. So, both are gas and platinum oxide you get. This procedure involves first preparing a platinum nitrate, which is then heated to explain nitrogen oxide. So, this you have to heat. Platinum nitrate, if you heat, then platinum oxide, nitrogen dioxide and oxygen is formed. Examples, hydrogenation, it is mainly used. Here you can see 1 atmosphere hydrogen platinum oxide, you get this. So, this is syn addition, the hydrogenation is happening. So, syn addition only possible here, and Dr is 95:5. Here in alpha beta unsaturated ester, here it is an acid alpha beta unsaturated with H2PtO2 acetic acid. So, photic solvent you have to use, and you get this. So, here also syn addition is happening mostly, and from the bottom phase. So, attack is taking from the bottom phase, attack. And in this case also the cyclohexanone, here methyl is there, 3 methyl groups, but this is in axial. So, this will block the top phase. So, reduction will take place from only bottom phase. So, bottom phase attack here also, and you get this product as a major in 83%, and this is the minor 17%. So, not only the double bond, a carbonyl also can be reduced with this platinum oxide hydrogen system. This is a triple bond reduction. So, here is H2PT platinum oxide only, and then you get this triple bond reduction as well as the propargylic OH group. So, this also removed. So, this is important. This OH is further this staying, but propargylic alcohol is getting removed. So, reduction of aromatic compounds is also possible here. Pyridine motif is there, H2PtO2 ethanol, you get this piperidine motif, and then you can cyclize to get this bicyclic compound. So, now we will discuss the iridium based reagents, and one important reaction the iridium carries, that is the photocatalysis. So, redox catalysis. So, this is the catalyst structure. This you can see, this is PPY group, PPY, and this is DTBPPY, this one, and PF6 is the anion here. And if you react with this NRI tetrahydroisoquinoline with this catalyst only 1 mole percent nitromethane AR and 15 watt CFL lamp, then you get this product. So, this is the CH2NO2, that means the iminium ion is formed. So, this is via iminium ion intermediate. You get this product in 90 to 96% yield. So, what could be the mechanism? No, this is the starting material, this is the lamp, and you can see this is the iridium 3, and after lamp only it is getting activated iridium. So, this is the activated, and in this activated iridium only it can do the reaction. So, after reaction, photoredox catalysis, you get this radical cation. So, this is 2 is radical cation. Radical cation is formed by reductive quenching of the excited state, forming the powerful reducing agent iridium 2 plus. Catalyst turnover may be accomplished by the reduction of nitromethane to its radical anion or an advantageous oxygen, and which will, this can be also CH2NO2 also possible, minus dot, and this will deprotonate this one. After that, this iminium ion will form. So, this is the iminium ion, may abstract and form the trialkane ammonium radical cation to form the desired iminium ion, and addition to the iminium ion forms the observed product. So, nucleophile is adding to the iminium ion. So, this is the single electron transfer process is happening here. One electron is taken by iridium 3A and it is going to iridium 2, and now again the oxidation is happening of iridium 2, it is becoming iridium 3. So, this is iridium 2, iridium 3, and after activation by light it is becoming the star. Iridium star means that is the activated iridium, and this was published in JOC 2016 6898. Also, an oxidation can be possible with iridium. So, this is the oxidation of alcohol. Here secondary alcohol is used. So, secondary alcohol is going to carbonyl compound and H2 is eliminating in this process. So, this is the catalyst CP star iridium, and you can see there is a OH group. So, this is the acidic hydrogen that is important for the reaction. Acidic hydrogen is present, and cyclopentadiene star group is present there. So, what could be the mechanism? So, when a metal complex A ligated with a ligand bearing a protic functional group could be employed, a metal hydride C should be formed via metal alkoxide B. So, here metal LXH, so XH is the OH here you can see. So, this is the acidic hydrogen, and now the alcohol will coordinate to the metal like this will form, and now this metal hydride. So, this hydrogen will come to metal now, metal hydride species is formed and the oxidation is happening. So, main thing here, the metal is coordinated to the ligand as well as the alcohol, and in this process one molecule of hydrogen is liberating of course. Later the one molecule of this one C can liberate one molecule of hydrogen, that is the ligand promoted dehydrogenation. So, on the metal with the protic, then an intramolecular reaction of the hydride on the metal with protic hydrogen on the ligand could readily take place to facilitate the release of dihydrogen. So, from this metal hydride after elimination of a hydrogen, because this hydrogen is important now, because after this hydrogen only it is going to hydrogen gas. The resulting hydride free metallocycle D, this will form metallocycle D will react further with an alcohol. So, if it reacts with alcohol further, then it will generate B. So, this is the active component actually, this is the active component of the catalyst system. This was published in Organic Letters 2007. So, today we have seen first the nickel catalyzed reaction. We have seen defined reaction with nickel, that it can do the carbonylation reaction, then tetramerization 2 plus 2 plus 2, that is the Reppe synthesis we have seen. Also we have seen 2 plus 2 plus 2 reaction with benzene. So, you can get naphthalene derivatives. Then we have seen different CC bond formation reaction. We have seen the 3 component reaction, alkyne and enone as diethyl zinc. There you can get the products, and when the enone and the alkyne is in the same molecule, then you can get another cycle product. And all cases we have seen the zinc component, that is the like dimethyl zinc, that methyl group as to the syn fashion of the newly generated double bond. This geometry is observed all cases. Then we have seen the nickel catalyzed cross coupling reaction. So, that is an important discovery by Nochel, who used the first the olefin in the substrate, and that case the Kumada coupling worked nicely. Then he used CF3 containing styrene, and that has been used an additive, and that cases you can also use the substrates which does not have double bond, and all are alkyl, that is alkyl iodide as well as the alkyl Grignard, and you can get this product. Then Kembe came up with 1,3-butadiene, and he found that this can be used for the Negishi cross coupling reaction with zinc, and defined alkyl zinc and alkyl iodide, bromide, tosylate, even fluoride also can be used. Also fluoride case, he has found that if you have a additive where 2 diene system is there with the malonate group, that is found to be better and giving the product in high yield. Then we have seen the platinum catalysis, and platinum we have seen the reduction of double bond. We have seen that platinum is the active catalyst here, because after reaction with hydrogen, that is the platinum is forming, and that is the active catalyst. And lastly we have seen iridium catalyzed photocatalysis. We have seen nitromethane addition to isoquinoline and oxidation of alcohol to ketone, that we have seen. Thank you.